Now, today we will study about other material properties. Well, take a look at this bar. This bar will expand not only in this axial direction, but also it contract in these transverse directions. That's what happening in a bar. That is different from spring. Spring, we didn't care about the side contractions. But we have a bar subject to, let's say, P like that. Then depending on how much delta here, we just say P equal K delta. That's the definition of a material property in x directions, right? That's just K. In spring, we don't care about transverse contractions because the spring always works for axial deformations. But in a bar or solid, these contractions plays really important role in stress and strain distribution inside the body. So we have to define a material property. Actually, the amount of contraction depends on the materials. Say aluminum, steel, rubber. It depends on what kind of material. The amount of contraction is different. Then how we define this contraction, this amount. Total amount, let's say delta y. This is called delta x, and this is delta y. Total deformation, delta y. Well, delta y is certainly depends on this length, Ly. Right? Depends on Ly. So we have to, so when we define the ratio delta y over delta x. Okay, this delta y is proportional to this deformation. Means that if we have more deformations in x directions, this delta y will have more contractions. So we have to use the ratio between delta y and delta x. And also this delta y depends on the Ly length. So we have to use Ly, and delta x we have to use the Lx. Okay, this is the material property we call Poisson's ratio, mu. And since, okay, I will review again. This delta y, the delta y depends on material properties, and delta y is proportional to this delta x, and also proportional to this length Ly. So we have to use use definition of normalization Ly, and also in this direction we have to use normalized deformation. So this ratio is the material properties. Okay. Again, Poisson's ratio, the y direction strain. In x direction strain, we defined delta x over Lx. Why we define strains? Why we define delta x divided by Ly? Well, materials properties means that if we have this much length twice, this delta x will be twice again. So we have to use normalized by this ly. Then this is the definition of, epsilon y is the delta y ly. Similar to a x directional strain, epsilon x equal delta x divided by Lx. That's the axial strain. Similar to an axial strain, we are defining y directional strain. And then the ratio between epsilon y and epsilon x is called Poisson's ratio. So Poisson's ratio, we define epsilon y divided by epsilon x. Well, that is simply delta y divided by ly, delta x divided by Lx. Well, there is a minus sign there because when this bar is extend in y direction, x direction, in y direction it always contract. And this epsilon y, so delta y should be negative, and this is a negative, but the material property is better to be defined as a positive value, so that's why we are using a minus sign here. So anyhow, epsilon y is defined as minus Poisson's ratio mu times epsilon x. That's the definition of Poisson's ratio. As he said, the minus sign is used because of the positive material properties. Now still, how about the material property for real materials? For the steel, the Poisson's ratio is 0.28, and aluminum is about 0.33, and rubber material property is 0.45, very close to a 0.5. Okay, very close to a 0.5. And this one, approximately, we can say Poisson's ratio is 0.3. So almost all metal material property which has the Poisson's ratio is 0.3. Okay? So when you solve any problem, you just assume 0.3 for any metal. That will be quite enough. Okay, that's the, so remember that we have two material properties, Young's modulus and Poisson's ratio in a bar, which is different from a spring. So we have two material properties, Young's modulus and Poisson's ratio, in a solid. Okay, in solid. Well, this is the today's report. Okay, let's move to next lecture, lecture 5, stress, strain, and material properties. Well, this is just continuation of the Poisson's ratio and Young's modulus. We just define a stress and strain in axial directions or in transverse directions. Well, here we, as I mentioned, we have three different structures, bar, beam, and shaft. And this one, well, let's just forget about those three structures. And this chapter, we will review general behavior of solid. General behavior of solid. It has generally, it has a three-dimensional shape. And here we will define general behavior of the material, which is displacement and strains and stress. How do we define strain and stress in three-dimensional space. Well, displacement is simply defined as, let's say we have a structure like that, and it moves from one point to the other, and then displacement is simply consists of, classified into a translation of a point. Okay, move can translate, and rotation of lines, change of lengths, elongation, and contractions, and distortion, which is the angle change between lines. So let's say we have a this is the original configurations. This is the original configuration before deformations. And this is the deformed shape. This is the original, and this is deformed shape. Originally there was the A and B, and after deform, it moves to A prime and B prime. This is the line before deformations, and this is the line after deformations. And this line has 4 different kinds of displacement. This line can translate, and this line can rotate, and this line can extend, and this line actually distort. Distort cannot be expressed by line. Distort means that if we have some original body like that, and this one will have something like this. And as you can see here, this angle or that angle here, this angle and this angle is different. That means body is a distort. So again, displacement consists of 4 different things: translations, just bodies move, and rotation of lines. And as you can see, this line is rotate. And change of length. Well, this length is extended here. And distortion, this angle has also changed. Well, we will define those displacements in using a coordinate system. But I just want to give you why we need to define what the displacement consists of. In 3-dimensional body, we can define 2 different types of strains. One is the normal strain. Normal strain means that when we define material properties in Young's modulus, we define as delta divided by L. That is the axial strain. Sometimes called normal strain. this is the same definition, axial and normal strain. So when this bar is subject to axial load, this will expand in delta in x directions, and delta divided by L is called normal strain. But another deformation is the distortions. As you can see here, this rectangular, so still rectangular, means that this angle still same as before and after. But here, the length is the same. Okay? Before and after, the length is the same, but this angle, or this angle, the angle has changed. So we have to define a strain which describes the angle changes. So that is called shearing strain. So shear strain is defined as the angle changes. As you can see here, shearing strain is defined by the angle phi, okay, this phi, tangent phi, and in terms of displacement, this delta S divided by L, this divided by L is the tangent phi, and that's the definition of the shearing strain. And this is the definition of the axial strain. Again, this normal strain is very much similar to spring deformations, but this one, we cannot define this shearing strain in spring. This is happening only in two-dimensional space. And stress-strain temperature relations okay, we define a Young's modulus E, and I already explained how we measure this E using strain gauges here. We attach a strain gauge here, and then we apply the force, and force divided by A will be defined as a stress, and deformation delta divided by L will be as epsilon. And this one is usually, is defined as the Young's modulus. And real material, what's happening is that this is up to here is the just linear ranges. So stress is defined as E and epsilon. But after some yielding, we have a large plastic deformation. And here we call elastic. And you just have, I just want to know that there is some plastic deformation after some yielding. But in this course, we will cover only elastic zones. And Poisson's ratio, as I mentioned, this is the contractions. And another material property we will define, okay? This is just a review of material properties, and we will define this shear modulus again. And shear modulus has the relations. See, this one is subject to some stress. Well, what kind of stress is this? Well, we will define. I just want to know that there is some way of defining shear modulus. This is called tau, and this is the gamma. So tau is defined as the gamma, G times gamma. And that is called shear modulus, very much similar to a stress E epsilon. And this Young's modulus and this shear modulus has some relations, is like that. Again, we will define and we will go through in detail later. I just want you to review of the material properties. Okay, this is the stress-strain relations, but the materials also extend in when this material subject to a temperature. In other words, let's say we have a material like that, and we apply delta T, and this one will expand in every directions. So how do we define the material property relate to this thermal strain? We call it thermal strain. This is the how we define material property alpha. So depending on materials, let's say this is the material steel or rubber, the amount of extension will depends on materials. So the way we define the strain is the epsilon. Thermal strain is proportional, always proportional to a delta T. So delta T times alpha. Alpha is called coefficient of thermal expansion, CTE. CTE. So whenever this bar is subject to a force P, and this material is also subject to a delta T, then this bar will expand because of this stress, sigma, and it will also expand because of this temperature. So total expansions, total expansion will be given in terms of stress. So remember, stress equal E epsilon. So epsilon will be sigma divided by E. So this is the expansion due to a stress, and this is the expansion due to a temperature. This is the summation of strains. It's called total strain. Well, I have to reorder this slide. The slide is somehow mixed up. But anyhow, just to remember that in solid, we have a material properties, Young's modulus and Poisson's ratio, and CTE. Okay, those are three material properties. And shear modulus, we will define later. We will define these shear strains and shear stress. Okay, don't worry too much about definitions. But I just want to know that there is the shear modulus relating this shear stress and shear strain. And that is the another material properties, but there is a relation between Poisson's ratio and Young's modulus. And G is the shear modulus, and G depends on those two material properties, is not independent material properties. So anyhow, this is just a general review of the material properties. And now back to here, we have a displacement and deformations. Okay, stress in two-dimensional case is very much similar to an internal force. We define internal forces. Let's say we have a body like that, and this is a subject to an external load. Okay, external. They are called external load, right? And if we cut through any plane, we have two bodies. We will have two bodies. And inside what will happening here, we will have an internal force. Internal force will be in force equilibrium with external force. And this body we can have also a different cutting like that. And same okay, what we are trying to do is that we define stress at this point O. This point O. If we take a look at here, we just cut a arbitrary cross-section here, and these cross-sections is defined as the normal vector n. And this one also has the perpendicular direction, which is called direction t. So we can cut either this way and this way. Of course, we can have many different ways of cutting, but we just consider two perpendicular directions, and this one and this one. Those two directions are perpendicular, n and t. Now, what we are trying to see is that what is the happening in these cross sections. As we know, since we have an external force here, and we should have some internal force here to have force equilibrium, right? These, whatever internal force there, these internal force should be in force equilibrium with the others. And same for here. Okay, same for here. We have the cross sections like that, and we will have internal force in this direction. But here, the most important point is that the direction of the internal force is not always perpendicular. This internal force can have arbitrary directions, this way and that way, whatever directions. Am I right? Depending on this external force, these internal forces can have arbitrary directions. So to denote this internal force, we will decompose this component into normal directions and shear directions. That's why we have a component this way and that way. And same for the other directions. We have the internal force. We can have the internal forces like that, and we can define normal and shear, normal directions and tangential directions. In one-dimensional case, okay, if we cut here, if we apply force like that, then always there is only internal forces in normal direction. That's what we have considered. We never consider in tangential directions, because we know that this force, the internal force, will not be like that. The internal force will be always same direction as this as this one, right? That's why we always consider internal force in same directions. But in general case, this internal force can have this way depending on how much force we apply here. So this is the general definition of internal force. Internal, at any cross section, we can have component, perpendicular direction and tangential direction. Same here, normal direction and tangential directions. Okay, now here at point 0, before we cut, at point 0, we have 4 components of internal forces, which is this one, that. So 4 components. Again, in one-dimensional case, if we cut here, we only have one component of internal force. Okay, only one component internal force. We define that internal force is P divided by A. That was the only one definition. But in two-dimensional case, the cross sections can have 2 different directions. That's the 2, and each direction we have a 2 component. So twice of times these 2 times 2 give us 4. So we can have a 4 component at point 0. Well, that's why this stress or internal force at one point we have 4 components. Sigma here is sigma NN. Okay, sigma NN, and this one we call sigma TN, and this one we call sigma TT, and this one we call sigma NT. Pay attention to this subscript. Okay, this subscript. This is TN, NN, TT, and NT. These force index N and T comes denote this force direction. This is the N directions, okay, this N direction and this T direction. This second index NN, okay, this second direction N. Why we have the N here? Because this cross section is the N directions. This area is denoted by this N. Here, these cross sections is defined by this T. That's why we have the second index T, and this one is the T directional load, and this one is the N directional. So again, we have this 2 by 2. This one and this one. 4 components. Okay, let's extend to a little more general case, 3-dimensional case. Three-dimensional case. Again, the concept is same as 2-dimensional case. We are trying to define an internal stress at a point O. Okay, at a point O. Internal stress at a point O. First, how many cross-section can we have in 3-dimensional space? Well, again, we can have an infinite number of cuttings. But here, we can have 3 perpendicular axes, and we can have 3 different sections. Each one has the N, T, and M. Okay? N, T, M. Now let's we cut these sections with N. And we can also cut here is a T. We also cut here is a M. Okay, compared to the other one, is very much similar. Here we have two directions, N and T. We can cut here N. This is called N directions cutting. And this one is called T direction cutting. Okay? This is what? N directions. And this one is T directions. So cutting always can be denoted by these directions normal to this cross section. So N and T. So again, this is N and T and M. Now, how many stress or force component can we have in each direction? For instance, this N. How much forces can we have? This N, this cross section only. Well, in general speaking, the reaction forces can be any directions. And these directions, these forces will have three components. This. That's why in general sense we have three components. Again, this summation of this one will have arbitrary direction and with some magnitude. So this internal force will be represented by these three components. And pay attention to these three components. This one, this is the N direction, right? This is the N directions. Pay attention to here, N. Now I'm going to call this one this is the sigma N, N. And this one is called sigma T and N. And this one is called sigma M and N. And this second index, what does it mean? It means these cross sections. Okay, second index is meaning these cross sections. And fourth index, what do they mean? T and N and M. This fourth index means that the direction of force, right? Direction of force. N and M and T. So we have these three components of stress in a plane denoted by N. Three components. Well, exactly the same for the other cross sections. T, again, we can have arbitrary forces, and which can have three components of forces. And since it's a T, this one will be, this force is in T directions, and this one N directions, and this one is M directions. But again, since these forces are in N directions, we add another index to differentiate from other components. Now, the third one, well, the same. Three components of forces. In this cross section, we have another three components. So again, at this point O, we have noticed that we could have 9 components of forces or internal forces depending on how we cut. Okay, how we cut. So we, as you can see here, we have 9 components. 1, 2, 3, for these cross sections. And here, again, 1, 2, 3, and 1, 2, 3. You may ask, what if we want to cut in the other directions? Well, as long as we have this 9 component of stress, 9 component of internal forces, we can always calculate internal forces at other directions. So don't worry about the arbitrary cross-section. These are already arbitrary, and each cross-section can have a 3 component of a stress, and that's why the stress at a point in 3-dimensional space, we can have these 9 component of stress. And these 3, okay, pay attention to those 3 components. They are different from other components. Those 3 components are different from the others. What makes them special from others? Well, this one, NN, TT, MM, first of all, these 2 index, they are same, NN, TT, and MM. What does it mean? It means that this is the N directions, force directions in N plane. So I would say sigma ij, this is the force directions, and this is the area directions, right? So NN means that force and area direction is the same. This is the area direction, and this is the force direction. This is the area direction, and this is the force direction. This is the area direction and force directions. Means that those 3 components is always normal. Normal to cross-section. Normal to cross-sections. Okay, normal to cross-sections. This is a normal stress. Other stress, these 3 and these 3, totally 6 components, the index, NNM, NT, TM, and they are all, the 2 sub-index are different from each other, and that means force direction and cross-sectional area direction, they are different. Means that in here, Tn, we have an N direction, and this is the T direction, or this is M directions. So those 2 directions are different from this normal direction. Same for this NT and MT. This is the T direction, but this is N and this is M. This is M direction, this is the N and this is the T. So shear stress, they are called shear stress. Shear stresses are in this off-diagonal term. So this is the diagonal terms. This is the off-diagonal term. Well, same for this. This one, they are normal stress. Normal stress means that this one and this one. See, index NNTT, same subscript, and they are normal stress. And this is the shear stress. Well, you may wonder why we are bothered by such a complicated definitions. Well, hard to explain at this point, but just try to understand the definitions in this way, and you will see why and how we define material properties and how we define, this is the how we define internal stresses, and later on we will define strains, and later on we will define material properties in three-dimensional space. Okay. I will just summarize for you. Okay, I will just summarize the stress in one-dimensional case and two-dimensional case and three-dimensional case. In one-dimensional case, again, this one, we only have one component, which is sigma x. That's it. Well, in strictly speaking, we have to use the two subscript. Okay, this is the x. This is the x. And if we cut it here, we only have this one component. What is these directions? Since this is x, will be the x cross sections, right? This is the x cross section. And what's the direction of a force? Also x directions. And that's why we use the sigma xx. In other words, we're not going to have this component. If we do, this would call, since the x is x and y, this component will be called sigma yx, right? But in one-dimensional space, we're not going to have that kind of internal force. Why? Well, we have only x-directional external force. We're not going to have this much internal force. Am I right? So we only have one component of stress, internal force. Well, this is a stress. Well, you may say this is the internal force. Internal forces. But in two-dimensional case, okay, two-dimensional case, the situation is a little more complicated. And here, this is subject to this force, and that force, and that force, many different forces. And at this point, we can have this cut, and that cut. And as you can see here, this sigma, we can have sigma xx. Let's say this is the x and this is the y. And if we cut x, we have sigma xx and sigma yx. If we cut here, we have this force and that force, sigma xy and sigma yy. I mean, just like we have defined. And 3D case, at the internal force at one point, we can have, see, this one is the x and y, and this is a z. At the internal force at one point, we can have sigma xx, yx, sigma zx, sigma xy, sigma yy, sigma zy, and sigma xz, sigma yz, sigma zz. Just, I want you to notice that along with these space, one-dimensional, two-dimensional, three-dimensional space, we have internal forces, or this is called stress. Stress can have one stress component, 4 component, and 9 component, depending on the space. Okay? And later on, we will define this deformation. Later on, we will define strain. Strain is simply L divided by delta, right? This is only one component, similar to P over A. We have only one component, but in two-dimensional case, we have 2 by 2 and 3 by 3. And material properties, we will define stress equal E epsilon. And for two-dimensional case, we define this stress and strain, and this stress and strain. We will define material properties relating these stress and strains. Okay, the reason I summarize this way is that it's very much similar to F equal Kx. F is what? In spring, we have the force and deformation and material property. This is the internal force, and strain is in deformation, and material property will be Young's modulus. Okay, we will expand the concepts like that. Okay, sorry, it's already 20 to 30. Okay, that's what we're going to cover today. And okay, let's see you Thursday. Okay.